So what we need to do by the end of today is make sure that we can use oxidation numbers to balance equations. So you'll come across in your exams questions ask you to do that, and basically they are redox reactions. So what you can't do is just look at the atoms present and balance for atoms and assume you've got the right equation. Sometimes it works, but often it doesn't, because you know that when we've been combining half equations to come up with overall equations, you've often had to multiply one of the equations up, so you've got the same number of electrons in each half equation. So effectively what we need to do is factor that into our balancing. We also need to be able to write equations when we're just told that something happens in acidic solution. So we need to use that information and know that if we're in acidic solution, we've got as many H+ ions and water molecules as we need to balance the equation. And if our reaction is in an alkaline solution, we've got as many hydroxide ions and water molecules as are needed to balance the equation. But we need to look at how to actually do that. So we've got a couple of examples on here where we're actually coming up with half equations. And then on the other side, we've got one where we are just going to try and come up with an overall equation straight off as well. So these two are going to come up with half equations that we're familiar with, we've used before, but it's kind of showing how you work it out. So if we need to write an equation for MnO4- ions being reduced to Mn2+ ions in acidic solution, we're going to break this out into kind of 5 steps. You'll get to the point where you can just do it in one go and not have to write out loads and loads of lines. But the thought process is exactly the same. So we are going to start with MnO4-, and that is going to react to form Mn2+. So the first thing we need to do, this is just going to be a half equation because it's not saying it's reacting with anything, is to look at the change in oxidation number and work out how many electrons are being transferred. So what's the oxidation number of the manganese in the MnO4-? Yeah, so you've got +7 there? Yeah, okay, so remember each of the oxygens is -2, which gives us -8, but we don't write -8 down because that isn't the oxidation number. We write -2 down. But -8 to -1, we need to add on 7. So the Mn there is going to be +7. So we've gone from +7 to, what's the oxidation number here? +2. Remember, Mn is simple ion, it's just the charge on its ion. And so have we lost or gained electrons? Gained electrons, good, because if we are getting from +7 to +2, we need to put some negative stuff in. How many electrons? 5. Yeah, so we can say here we've gained 5 electrons. So then we can develop our equation a little bit more then. So we now know that MnO4- needs to gain 5 electrons in order to become Mn2+. So we're now balanced in terms of our oxidation numbers and our electrons. So what we now need to do is look at actually balancing the rest of the equation. Now we can look at the left hand side and see we've got oxygens on the left but no oxygens on the right. So now we've got to remember that we're in acidic solution, so we've got as much H+ and H2O as we need to balance the equation. So if we've got 4 oxygens on the left and none, we can put in 4 molecules to provide us with those 4 oxygens there. So we can have MnO4- plus 5 electrons that we had before going to Mn2+, but we're now going to add on 4 H2O. So our 4 H2O that we've put in balances out the 4 oxygens we've got on the left. But now we've thrown in a load of hydrogens that we don't have on the left. So we need to account for those. But again, remembering we can put in as much H+ and H2O as we like. On the right hand side now, we've got 8 hydrogens. So we will balance that out by putting in H+ ions. So we'll put 8 H+ ions on the left hand side. So the bit we're adding in here, I'll just kind of underline the bit we're adding on at each time. Plus 8H+, so I'll put that on as new. And that's our 4H2O. So now we have balanced for the oxidation numbers and electrons. We've balanced for the atoms So our equation ought to be correct now. And final check, and if you've got this final check right, the chances of you getting the actual equation wrong are pretty minimal, is to double check that we've balanced for atoms, and then to check that we've balanced for overall charges as well. So the net charge on the left must be the same as the net charge on the right. So we've got 6 negatives, 8 positives, so that gives us 2 positives in total. And we've got 2 positives on the right, so we've balanced for charges. And then if we check through 1 manganese, 1 manganese, 4 oxygens, 4 oxygens, 8 hydrogens, 8 hydrogens, we're balanced for atoms. So that ought to be correct. And that is the half equation for the MnO4 minus sign. So that's one we've been using when we've been quantifying the amount of Fe2 plus in a solution. Yeah. Now, I certainly wouldn't expect you to write all these lines out, but that's the thought process. That's what we need to go through when we're doing this kind of question. So we'll have a look at the next one. So this time we've got Cr2O7 2- being reduced to Cr3 plus in acidic solution. So we're going to write down the correct formulae. Now in this particular one, can you see that on the left-hand side, we've already got 2 Crs. So what we know to start with is that for each one of these, we're going to always need 2 of these. So these proportions are fixed. So it's worth kind of making sure we put that 2 in there. Often it's questions that have iodide ions and iodine that you need to make sure you always have of 2I minus for every 1 iodine and so on. It's just worth watching and often trips people up. So we need to find the change in oxidation number and hence the number of electrons transferred, bearing in mind that we've got multiples here as well. So what is the oxidation number of the chromium in the dichromate here? Yeah, we've got +6. So each of our oxygens is -2, giving us a running total of -14, which we don't write down because that isn't the oxidation number, it's -2. Cannot emphasize that enough. We've got to get from -14 to -2, so we need to add on 12, but that's split between the 2 chromiums. So the actual oxidation number is +6. So what we need to do is go from 2 lots of +6 to, remember the oxidation number is just +3 over here, to 2 lots of +3. So have we lost or gained electrons? Gained electrons, how many per chromium? Yeah, 3 from the change in oxidation number. So how many electrons have been gained in total to make our equation? We get the 6 because we've got 2 lots of going from +6 to +3. Okay, so we can then say, I'll put it as 2 times 3 electrons gained, so you can just see that it's become doubled up there. So we can now add that on to our equation. So +6 electrons on the left going to the 2 Cr3 plus on the right hand side. And then our final steps are the same because we had an acidic solution again. So we need to add water molecules in order to balance the oxygen atoms. So we've got 7 oxygens on the left hand side, but no oxygens on the right hand side. So we're going to have 7 waters. So +6 electrons goes to 2 Cr3 plus, and our new bit now is our +7 H2O. And then we can add in hydrogen ions to balance the hydrogen atoms. So we've got 14 H's on the right hand side, but none on the left hand side at the moment. So we're going to go and pop those in. So it's +14H plus goes to 2 Cr3 plus +7 H2O. And we could underline those so we know we've just added those in. And then to double check we've got our equation correct, we need to check its balance in terms of charges and the atoms. So we've got 2 negatives and 6 negatives gives us 8 negatives. Add on 14 positives gives us 6 positives in total. And then on the right hand side, we've got 2 times 3 positives, so 6 positives on the right hand side. So we're balanced for charges. Check the atoms. 2 Crs, 2 Crs, 7 Os, 7 Os, 14 Hs, 14 H, balance for atoms. And as I was saying before, the chances of you actually getting all that right and still getting the equation wrong is pretty minimal. Okay, so you should be safe then. So it's a really good way of double checking. Be okay with that so far? Okay, so whenever we're doing this with half equations, obviously you need to make sure you've got your electrons showing. Clues in these questions that we're just saying one thing being reduced to the other. It's not reacting with something. So that's kind of indicating that that would be a half equation there. Now, on the right-hand side, we're looking at full equations now, and there are two different ways we can do this. Okay, so you can separate out your reaction into its two half equations. Do exactly the same process that we've just done on the other side of the paper and come up with two correct half equations and then scale them up for the number of electrons needed and then combine. Or you can just go for it. So I'm going to show you the kind of just for it method because that's probably where you want to get eventually, because it's a bit kind of faffy having to separate them and then recombine them. So first thing to do is write down the correct formula of the species involved. So this time we want to know about the oxidation of sulfide ions to sulfate by dichromate ions here. So on the left hand side we're going to have the Cr2O70 minus reacting with our sulfite ions, producing sulfate ions, and I hadn't added it on, but it's Cr3 plus, just like we did before. Remember that because the dichromate has the two chromiums, that however many of these you have, you will always need two of those. So I put the two in there to start with. So any scaling up we find we might need to do will be with that two in. So what we then need to do is find the changes in oxidation number and the number of electrons transferred for each of the half equations that are involved here. So for the dichromate going to the Cr3 plus ions and for the sulfite going to sulfate. Okay, so on the other side, we already looked at the chromium and we said we had two lots of +6 oxidation state, went to lots of the +3 oxidation state. And we've already decided that that meant 3 electrons were gained in total there. What about the sulfur? What's the oxidation number of sulfur in sulfite? So have a look at this one here. We've got +4. Okay, so remember each of the oxygens is -2, gives us a running total of -6. To get from -6 to -2, we add on 4, so it's +4. What about on the other side, the sulfate? Yeah, that's the +6. Okay, so our sulfur has gone from +4 to +6. So is it lost or gained electrons? Lost. How many electrons? 2. Okay, so we've got 2 electrons that have been lost. So we have got one process that is a 6 electron transfer and one process that is a 2 electron transfer. So what do you suppose we're going to have to do first of all? I think I heard the right murmurings at the back there. What do we need to do? Times? Yeah, so we need to times the second one by 3. So just like we would if we were looking at half equations, this second equation, we're going to need 3 batches of this for every one of the top. So we need to note down at the side, so multiply this one by 3. Okay, so that is going to mean that we've got Cr2O70 minus plus 3 SO3 2 minus will is 3 SO40 minus, you see that's a 4, plus 2 Cr3 plus. And that means that we've got 6 electrons being transferred per equation here. So then, just like before, we need to throw in the water molecules and the H plus ions. The only difference is that this is going to be an overall ionic equation, not a half equation, so we don't have any electrons showing. The fact that we've scaled up here has sorted out the electrons for us because we've got as many being lost as we have. So how many oxygens have we got on the left hand side? Yeah, spot them all. So we've got 7, and then 3 times 3 is 9, so that was 16. How many on the right hand side? Providing you can read my numbers. 12. So how many waters do we need on the right hand side? 4. Okay, so again, we can kind of put that down now, just adding in the additional bits. So was it 2Cr3 plus, and then what do we say, 4 H2O. Okay, and now how many hydrogens on the right hand side? 8. So how many H pluses on the left hand side do we need to add in? 8. So 3SO3 2 minus plus 8H plus goes to 3SO4 2 minus plus 2Cr3 plus 4H2O. And then the final step again, double check its balance in terms of charges and atoms. So on the left hand side, we've got 2 negatives and 6 negatives here. So that's 8 negatives, 8 positives. So there's no net charge. And then on the right hand side, we've got 3 times 2 minus, so 6 negatives, add the 6 positives here. So no net charge on the right hand side either. So that's looking good so far. 2 CRs, 2 CRs. What was it? 16 O's. 7 add 9 is 16 O's there. Then we've got 12 add 4 is 16 O's there. 8 H plus and 8 H's over there. All right, so this time that has come up with the overall equation. Now we'll have a go at the ones at the bottom in a minute. Just before we do that, I just want to show you how I would do this if we were going to try and not write out millions of stages. Okay, so if we were doing this same equation kind of straight off, then what I'd be inclined to do is write something like this. So you need to go in and put your oxidation numbers in. So we've got +6, +3, what do we have? +4 and +6 again. Then I'd put swoopy arrows in. So that transfer was 2 times 3 electrons. And then this transfer was just 2 electrons. And so we then need to look and go, right, that's 6, that's 2. So we're going to need to multiply this one by 3. So you can then just go and put your 3 straight in once you, and then you can go, okay, we've got 16 O's on the left, we've only got 12. So we go and put 4 H2O's in. We've now got 8 H's on the right, none on the left. So we can go and find a spot somewhere in there to go and put our 8 H pluses in like that. Okay, so that would be absolutely fine in terms of your working as well. So we've kind of methodically just gone through, so we've got lines that are saying think about this, think about that, think about the other, which you have to follow, and I followed every one of those steps doing this, but you don't have to write it out taking half a page to do every question kind of thing. All right, does that make sense? There's no no, so I'll take that as a resounding yes then, or at least maybe. Okay, so what I would like you to do next is just have a quick go at questions 1 and 2.